Hey there, it's Mr. Moydeen with our third distance lesson. This one builds on last week's regarding transformations, involving this time compositions of transformations. Let's see what that means. First, a little bit of review from algebra. If we're given that f of x is x squared and g of x is 3x plus 2, find f of g of x. Another way of writing this that may look more familiar to you, or maybe less familiar, is something like this. These mean the same thing, but what do they mean in the first place? If you look carefully at what this is saying right here, I'm going to color code this. This says f of, and in f's parentheses, the argument of f is g of x. So f of g of x. Order of operations in math says start with the parentheses. In this case, we have a innermost parentheses with x in it. And then that is living inside the red's parentheses, and that makes the entire quantity g of x inside the parentheses of f. So I'm going to replace g of x in blue there with what g of x is equal to. So we're given that g of x is equal to 3x plus 2. So I'm literally going to replace where it says g of x. I'm going to put in that space there what g of x is equal to, which is 3x plus 2. So there's f of g of x, f of 3x plus 2. Well, now what do we do? It says that the rule for f of something is that something squared. F of x is x squared. So f of 3x plus 2 is 3x plus 2 squared, according to the rule defined for f. So f of 5 is 5 squared. F of 7 is 7 squared. F of 3x plus 2 is 3x plus 2 squared. Well, we know our algebra, which means that we know that 3x plus 2 squared is the same thing as 3x plus 2 times 3x plus 2. We're going to do some double distribution here. Some of you may know this as something called FOIL, first, outer, inner, last. Whatever you know of it as, we're going to expand this by distributing 3x to both parts and plus 2 to both parts. So that'll give us 9x squared for this first portion, 3x times 3x. 3x times 2 is 6x. For the inner set, 2 times 3x is also 6x. And for 2 times 2, for the last distribution here, that will give us plus 4. So combining my like terms, that will give us 9x squared plus 12x plus 4. That would be f of g of x, or f dot g of x. Now this may seem to have no relation to geometry, but you'll see the connection in just a bit. This is called a composition of functions, putting one function inside the other, or applying one function to another. So in the previous video, what we learned last week was about the 4 major transformations: the translation, reflection, rotation, and dilation. We learned how to do a single one of those, so just translate, just reflect, and so on. This week we'll be combining them as mentioned, how to do multiples of them in the same step. So how do we do this? So first we're going to look at a couple visual examples, and then we'll do some algebraic or numerical examples. So I've hopped here over to Delta Math to do a couple example problems. This question says, determine a series of transformations that would map polygon ABCDE, that would be the pink one, onto A prime, B prime, and so on, which would be the blue one. So I first want you to kind of guess what the first step might be. And it looks like it might be a rotation, because it looks like you kind of take the pink shape and rotate its orientation. Notice that AE in the pink is vertical, but A prime, E prime in the blue is horizontal. So the orientation has rotated. So this was a rotation. It already gives us counterclockwise as the direction. So we're going to have to move, it looks like 270 degrees. And I'm just going to try to see if that works. So I know there's going to be 2 steps here ultimately, but I'm just going to try it. Okay. That isn't where I want it to be. So the next step would be looks like translation. It needs to move down. And if I look carefully here, it looks like I need to move down 3 units. So rotate and translate. Awesome. Rotate and translate. Let's take a look at this one here. Once again, taking the red or pink onto the blue. So my guess here would be, once again, if you notice the orientation here, it looks like probably a rotation because it kind of goes AB on the top in the red becomes the bottom in the blue. So let's just sort of do some guess and check here and do a rotation of probably 180. Okay, looks like it's pretty good. It's in the right orientation now. It just needs to probably do a dilation. With what scale factor though? So notice that the top segment here is 3 units long and then it becomes 1 unit long. Right, so it was 3, now it's 1, so that would be a scale factor of 1/3. So rotate. There we go. Let's do one more for good measure. See if we can get a reflection here. All right. So once again, taking the red and putting it onto the blue, let's try a reflection across the vertical y-axis. Let's see what that does. Okay. Looks like I should probably reflect it again across the x-axis. But then I would need a translation to move it down, but I don't have that option. So let's backtrack here. Let's maybe try a rotation of 180. Let's see what that does. Okay. So if I rotate 180, so that last step I didn't need, but if I then translate from the dotted step here, looks like it goes from -1 down to -8. So that would be down 7 units. So rotate 180. And there we go. So the goal here is kind of trial and error in some respects, but ultimately the better you understand it, sort of the easier you'll get it. Okay, so this is a similar problem, although it doesn't really look like it. It asks, what is the image point of 2, -3 after the transformation? I don't even know what that means. So let's take a look at what this says. This is actually very much like what we started with, looking at a composition of functions. This is our outer function and this is our inner function. So recall that earlier, something like this can be thought of as f dot g. And we started with this one and then we applied the outer function, right? So likewise here, we're going to start with this second function right here. What do you think the T stands for? Right, should stand for translate. So we're first going to apply the transformation along the vector 4, 5. So that means we add 4 to the x value and add 5 to the y value. In this case, both added because they're both positive. So if I do that to my given point, 2, -3 would become add 4 and add 5. So after the first step here, let me try to color code this a bit. After the blue operation, we end up with a value of 6, 2. We're then going to apply the second operation, which is r to 70. Now we have two transformations that start with r. They are reflection and rotation. Because it says 270, it should probably be a rotation, right? So we always assume counterclockwise. So the rule for a counterclockwise 270-degree rotation, if you recall the rule for that, is y comma negative x. So after the first step, we got 6, 2. So now we're going to apply this step to 6, 2. And if we do that, we should end up with, let's see, this says flip the coordinates. So y goes here and x goes there, and make the x negative of whatever it was. So if it was already negative, it becomes positive. So our final answer, after applying the translation and then the rotation, our final answer is this. Let's try a few more. What is the image point of negative 1, 3 after the transformation? Translate 5, 2 in composition with r, this time lowercase, y equals negative x. So which one do we start with, the t or the r? That's right, we start with the r. So this time it's a lowercase r. It probably stands for reflection this time because we have a line of reflection. So starting with that, the rule for a y equals negative x reflection, so this is a reflection, not a rotation. The rule for this is swap the coordinates and make them negative. So if we do that here, if we take the given coordinates and plug them in, we would get, swap the coordinates would be negative 3, 1. So if you look carefully, I swapped them and made them their opposite sign. The second rule is to translate by the vector 5, 2. So these are again both positive, so we're going to add to each one of these 5 and 2. So adding 5 would give me 2, and it's a weird 2. And adding 2 to the y value would give me 2 plus 1, 3. Did not mean to make that a vector. And there's our answer. So all this is what we did in the previous video, just two of them in a row, basically. First the second one, and then second the first one. Now, I want you to think carefully about something. Here, the particular problem said first reflect and then translate, right? Do you think the order here matters? Notice that this problem is the opposite steps. The point is the same. I haven't changed the point, but this time the order has changed. Do you think that it's going to give you the same answer or a different answer than before? Let's find out. So we're going to translate first this time. So translate along 5, 2. So if I plug in the points here, negative 1 plus 5 would give me 4, and then 3 plus 2 would give me 5. The second rule then is to reflect across y equals negative x, the rule for which is negative y comma negative x. So plugging that in here would swap the coordinates and make them both their opposite sign. So it turns out the order does matter. We got a different answer than what we got last time just by switching those. Last one. Here's our point. The rule is D2 combined with R90. So R90 here means a rotation of 90 degrees. So let's start with the second rule as always. So rotation 90 counterclockwise. The rule for that is negative y comma x. So plugging that in would give us negative 5, negative 2, negative yx. What do you think D stands for here? That's right, a dilation. Dilations require scale factors, and probably a safe assumption that the dilation scale factor here is 2. So just multiply by 2. And if we do so, we get negative 10, negative 4. And that's it. And we're done. Take care.